what he's not going to tell us.
Yeah, exactly. So, well, first of all, I have to say this is a great workshop, so thanks a lot to the organizers for inviting me and allowing me to participate. So I thought that was the best way to actually start my talk, because I've decided to change a little bit what I'm going to talk about, given the interests that have been discussed during the workshop. So in just 2 slides, let me tell you what I could have talked about, but I'm not going to talk about. So one of the things I was originally planning to tell you about is the question of cooling and entropy management. And that's an old paper that we wrote a long time ago with Jean-Sébastien Bernier and Corinne Collat, in which we proposed to create some band insulator at the center of the trap, which is a very low entropy state, and then reach very low temperatures by doing that. We've heard some related ideas yesterday in one of the talks. So that would have fit nicely the topic of the workshop, since it's breaking the ultra-cold barrier or something. But in the end, I decided I would not talk about that. Another thing that I would have happily talked about is the question of entropy transport, and this is something Tillman and I and Jean-Philippe Bantu and a bunch of collaborators did several years ago, which is revealing coupled transport of entropy in particles through the nice constrictions that they have at ETH. So anyhow, I'm happy to discuss any of these things, but I'm in the end not really going to talk about it. I thought I was going to talk in a somewhat provocative way about hot transport. So I'm sorry, perhaps it's not completely in the vein of the workshop, but what can we do with cold atoms that actually access the regime of high temperatures? And what are the fundamental questions that are there, especially with the condensed matter perspective, about the physics of hot transport? And if I have time, which is probably not very likely, I may talk about another hot topic at the end of the talk, which is a few remarks on the pseudogap. Okay, so the first thing I would like to mention, so what I'm going to say is based on, what I'm going to do is basically try to answer questions like that. What do we understand about bad metals? So we've heard about bad metals in at least 2 talks here, the talk by Wassenbacher and the talk by Brian DeMarco. So both talks actually advertise linear resistivity. So, it's a legitimate question to ask, should we be surprised? When should we be surprised about linear resistivity? And what are the regimes where we understand it? And then in contrast, when metallic transport qualify for being called strange, which is an acronym for not understood. Okay, this is a little quotation from my colleague Neven Barisic, who is a condensed matter physicist, who claims that resistivity is the first thing you measure and the last thing you understand, usually in any condensed matter measurement. Okay, what I'm going to talk about is based on 2 papers. One which is already a little bit old by Xiaoyu Deng and Marvlier and co-workers, which is an analysis of how you start from how the crossover happens from very bad metallic transport at high temperature way into the Fermi liquid regime at low temperature. And the second paper is a little bit more recent, and it's basically an attempt to set on solid footing what can be said on the very high temperature regime of transport in interacting fermion systems. And we pointed out in the conclusion of this paper that indeed doing the physics of hot transport with cold atoms is a great idea because of the reasons that are the obvious reasons, namely solids melt when you heat them too much, so investigating hot transport in solids is a problem. And more importantly, there are many other degrees of freedom that get excited at high temperature in solids, like phonons, which are also responsible for the melting, and are not there in the cold atom cell. Okay, so we've seen in this workshop actually talks about these two recent experiments, which are done in somewhat different ways. The experiment in the group of Brian and Marco is actually following momentum relaxation, so it's putting a little perturbation using a Raman process into the momentum of the two hyperfine species and looking at how this momentum perturbation relaxes. So it's a direct measurement of the momentum relaxation time. While in the group of Vasem, what is done is actually a density perturbation and watching how this density modulation, which is put into the system, relaxes. Both experiments in the optical lattice. Of course, what happens to momentum and what happens to density is ultimately related by the conservation equation. So these are two different ways of measuring things and reaching conclusions about, for example, the resistivity, which is reconstructed from the diffusion constant, the compressibility, as I will explain later. And you see here the data points of this paper, which reveals some sort of linear resistivity over an extended range of temperature that goes from perhaps about, I don't know, 0.3 hopping all the way to 8 times the hopping, which is the bandwidth in the context of this 2D problem. So, should we be surprised? When do we expect linear resistivity? Let me go back to very, very simple basic considerations. So let's start with a very simple Drude model of transport. So the Drude model, even though that's not how Drude formulated it, he had a very classical view about transport, but the way we think about it is basically we have quasi-particles, they have a certain mass, a certain density. We write an equation of motion for the velocity of these quasi-particles, and we obtain an expression for the response to the external field, which is dependent on frequency, and which involves the momentum relaxation time. Here, 1 over tau, which here is called 1 over tau Drude. Okay, so when we think in the Drude way, you see that the optical conductivity is just a simple Lorentzian, and it has a width, which gives me the relaxation time, and it has a weight, which is the plasma frequency, which gives me access to the carrier number if I know the mass. Okay, so you've heard in previous talk mention the so-called Mott-Jorferegel limit, so let me explain what this is. So basically, the question that Jorferegel asked, and Mott also asked a bit later, is when is at least the modern way of thinking of this question is the following. When is quasi-particle description legitimate, if at all? So when can we be, more precisely, basically certain that the concept of transport mediated by quasi-particles break down? So to understand that, it's useful to rewrite the Drude formula that I had in the previous slide in a slightly different way. Instead of the scattering rate, we can talk about the mean free path, which is just Fermi velocity times tau, and I can trade the density for the Fermi momentum using standard formulas. For example, in 2D it would be that. And if I do that, I end up into this formula here, which expresses the conductivity, or you may want to think of the conductance per plaquette of the lattice in 2 dimensions. So that would remove this lattice parameter here. So the conductance per plaquette, if you want, is the quantum of conductance, E square over h, times a dimensionless number, which is essentially KFL. So the product of the Fermi momentum and the mean free path. And basically, if KFL reaches a value which is of order 1, this means that the mean free path becomes nominally smaller than the lattice spacing. Hence, this would signal the breakdown of the quasi-particle context. And you see this happens when the conductance per plaquette of the lattice becomes, there's a little bit of Larsen effect, I feel, I don't know why. The conductance per plaquette reaches the quantum of conductance. So that's what's called the Mott-Jorferegel limit. And it has often been misinterpreted, saying that this should correspond to a saturation of resistivity. But in fact, as you will see in the following, and I think as is now well recognized in the community, this is absolutely not correct. The only thing that the Mortier-Feigl criterion is telling you is that the validity of a quasi-particle description breaks down when the Mortier-Feigl limit is reached, if not before.
Well, there's also the idea of minimal conductivity, that if it became lower than resistivity became
yes.
higher, it would become an insular.
Yeah, that's correct, but that's using the Mortier-Feigl criterion in a somewhat different context. So indeed, in the context of strongly correlated solids, we actually know many examples in which the resistivity, the system is a metal in the sense that the resistivity increases with temperature forever, but nothing happens when you reach this special value. So this is an example of a very well documented, probably one of the cleanest example of a transition metal oxide, and this is the resistivity versus temperature. And at low temperature, this system is a very good Fermi liquid with excellent metallic conductivity. And as you increase temperature, as you heat up the system, as you see, the resistivity continues increasing, and it happily goes through the Mortier-Feigl limit without any saturation of resistivity. So this is also saying that transport may not be the most insightful way to look into the system, because transport is not revealing here that quasi-particles die somewhere along the way. We need spectroscopic tools to actually understand that. Sorry, you had
What's the Fermi energy here?
Oh, the Fermi energy, so it depends what you mean by the Fermi energy. The bandwidth of the system is large, it's about 4 electron volts. The Fermi liquid coherence scale, below which you get T² resistivity, is 25 Kelvin. So orders of magnitude below, right? So, and the renormalization of the mass by interaction is about 5. It's a little bit like helium-3. Okay. So these are the questions I would like to ask. Should we be surprised that the resistivity can exceed the Mortier-Feigl value and the system still have metallic transport? What exactly happens at the Mortier-Feigl criterion? Indeed, from spectroscopic signatures, can we see that the quasi-particles actually disappear above T Mortier-Feigl? And of course, more importantly, we want to understand how to describe transport in the bad metal regime and also in the intermediate regime where the temperature is smaller than the Mortier-Feigl criterion, the temperature but larger than the Fermi liquid temperature. Are there quasi-particles in this regime, for example? And in which cases? Okay, so as I said, cold fermions in optical lattices are actually a great setup to answer these questions for the reasons I mentioned. There are no additional degrees of freedom, just particles and their interactions. They are clean systems, there is no disorder, or if you want to put in disorder, it can be controlled. And you can reach the high temperature regime without melting the system, so it's really an ideal setup to look at that. And one of the things I want to emphasize is that even though we've heard about transport in the high temperature regime in these two experiments, it would be really interesting to couple transport and spectroscopy to actually look more into the existence of quasi-particles. Okay, so let me start from the very high temperature regime and try to see whether we can make some control statements there. So is it possible to say anything about transport in the very high temperature regime from the techniques of high temperature expansions? And this is the second paper I mentioned before. So I'm going to consider the Hubbard model, lattice of any dimension, doesn't matter. The statements I'm going to present are very general. In the regime where the temperature is larger than the hopping, so that's an easy call for experimentalists, but much smaller than U. So we imagine we have this separation of energy scales. Most of the things I'm going to say is actually formally for the limit of infinite U, which applies to this regime. Okay, why is this actually difficult theoretically? You may think that understanding transport in a strongly correlated problem is always going to be easy in the limit where temperature is the largest scale. Indeed, if you consider a thermodynamic quantity, for example, the specific heat or the compressibility or anything, you can set up a high temperature series for that, and you can certainly get the first few terms of any thermodynamic quantities rather easily. And this is easy because the thermodynamic quantities are actually related to static equal time correlation functions. So you don't have to perform at the same time a long time expansion. However, transport is a different business because it's related to the low frequency limit, which means long time. And the regime you really want to say something about is the regime where frequency is smaller than temperature. CBR emphasized that many years ago forcefully. And this is not readily accessible for high temperature series. So, yes?
Why is that exactly? Because in principle I can do already the high temperature series by taking the infinite temperature limit of the diffusion constant and then basically doing what, and then times some compressibility.
Well, that's what I'm going to talk about this, but you can't set up, I mean, if you define the diffusion constant by the zero frequency limit, okay, you can't actually set up a high temperature expansion directly for that. The high temperature expansion will give you moments of the correlation functions. Yeah, but that's...
So it's a moment expansion.
It's a moment expansion, okay, and it's not an expansion for the DC quantity. That's the only point I'm making here. Okay, that's all I'm saying. So what you have to do is to actually set up a high temperature expansion for the moments of the correlation functions.
But still it would be frequency much lower than temperature because the temperature is infinite.
But the only thing you get are the moments. You don't get the DC value.
Why the first moment is not already infinite?
The first moment of what?
Well, usually
the first moment of conductivity is the kinetic energy. That's the F-sum rule, right?
The second one? Because formally if I do integrals, conductivity decays with some power law in omega, and if you multiply by omega squared, they're a little...
No, but that's only true within some range of energy. If you all the moments are
but if I go to infinite frequency, then I'm in trouble or not?
I
have to do something about it.
No, but you're alluding to I think you're alluding to the Drude behavior, right? But
even if it's not Drude, it's still some power law in omega. It's not exponential.
Well, in the Hubbard model, that's not clear because there is an energy U, right? And above the energy U, it's not necessarily power law.
I think not.
I think the moments expansion, the moments are well defined. Okay, so this is an example, thermodynamic quantities. That's very, very easy. You can do that on the back of the envelope. One guy which will play a very important role in the following is the compressibility. And you can just do that by just this very simple calculation. The compressibility is just by fluctuation dissipation related to the fluctuation of the particle number. And this is just easily derived in the infinite temperature limit. It's just something like n1 minus n, at least for u equal infinity. For finite u, it's also a simple formula. And you see that the compressibility, because of these 1 over T factors, behave like 1 over temperature at high temperature. Okay? And the kinetic energy, by a similar argument, also behaves like 1 over temperature. Indeed, the kinetic energy is just the expectation value of this operator, right? This has to be proportional to hopping itself, because in the limit of zero hopping, this would be 0. So this brings an additional power of hopping. Hence, this must be, since this is dimensionless, this must be hopping over temperature. Hence, this goes like T squared over temperature, right? So this just very simple thing shows that both the compressibility and the kinetic energy behave like 1 over temperature at very large temperature. That has been known for decades, of course. And it plays a very important role in the following. Okay, so now this is a much more non-trivial statement about the structure of the high temperature expansion for the optical conductivity or the frequency-dependent conductivity. What you can show is that the optical conductivity has a well-defined high temperature expansion which has this general structure. For infinite U, it's even a little simpler. Only odd powers of temperature actually enter this expansion. And what you immediately see from here is that the high temperature expansion of the frequency-dependent conductivity is entirely defined by these functions of energy of frequency over hopping, and these functions are completely universal function. They only depend on the density, right, in the limit of large U. Otherwise, they also depend on U over T. So just from this first expression, just by inverting and taking the omega to zero limit, if you give me that this function is going to be finite at zero frequency, you immediately see that the conductivity goes like 1 over temperature, and hence the resistivity goes linearly in temperature at high temperature, right? So this is a conclusion you can reach with completely independently of dimensionality, the lattice, or anything. It's a completely general result about the Hubbard model and any lattice model, actually, that the conductivity, that the resistivity at high temperature, temperature larger than the hopping but smaller than the interaction scale, behaves linearly in temperature, and a similar result can be established for temperature larger than U if anybody wants to get there, despite equilibration problems. Okay, an additional consequence, by the way, of this expression is that the slope of the T-linear resistivity, so this is, I think, on the next slide, this is the consequence of this expression for the resistivity. The slope in this regime diverges as you get to the Mott insulator. And this is something that, when after looks at other doping, would actually be interesting to look at. This only applies to this regime. For temperature larger than U, it's different than this. You can show that this slope is always reaching a finite value when you get to the insulator. So the behavior of this T-linear regime is different whether temperature is larger than U or temperature larger than hopping but smaller than U. There are two different linear slopes. Okay, so in this expression, rho naught is the Mortier-Feigl value, essentially. And what you see is that we are talking about resistivities here which are much larger than the Mortier-Feigl limit. So the conclusion of all this business is that there is nothing surprising in having linear resistivity in a regime of bad metal when the resistivity is larger than the Mortier-Feigl limit, and that really what runs the show is thermodynamics. So I'm skipping this because this is a more general proof. If I now decompose, which is what Ehud wanted to do, the conductivity into the product of the diffusion constant and the compressibility, which is just rewriting the fixed diffusion law in this manner. So this is the Einstein or Einstein-Nernst relation that we've also heard about in one of the previous talks, which expresses the conductivity as the product of compressibility and diffusion constant. I showed you in the previous slide that the compressibility goes like 1 over temperature, which means that the diffusion constant in the very high temperature limit, the very hot limit, goes to a constant. Okay? So what runs the show is the compressibility, and the reason you get T-linear resistivity at very high temperature above Mortier-Feigl is just because you're losing carriers, or if you want, the compressibility goes to 0. So this is the physics. And by the way, you will observe here that the diffusion constant in this limit has nothing to do with the so-called Planckian limit h bar over kt. It's actually a constant. Okay, so that was emphasized quite a while ago already by different authors and can be rationalized a very systematic way by these high temperature extensions. Okay. You can talk about compressibility. You can alternatively talk about carrier density, which can be defined from the kinetic energy, for example, and you reach the same qualitative conclusion because they all go like whatever temperature. Okay, so this sets sort of benchmarks for the high temperature regime. So now the question on the table is, what can be said about going below the Mortier-Feigl value? How does the resistivity behave there? Because the resistivities that have been measured in the recent experiments are clearly somewhat smaller than the Mortier-Feigl value. So for this, we need microscopic calculations, and there are not very many ones. There are some results that have been obtained by dynamical mean field theory. This has some long history. And there is a very recent Monte Carlo calculations in 2 dimensions by the group of Tom Devereaux and Stanford. So I'm just showing you here some of the most accurate DMFT results that have been obtained, in which what you see here is resistivity versus temperature, which is here normalized to units, which are the half of the bandwidth. So if you translate this to the 2D Hubbard model, that would be 4 times the hopping, even though that was not done for the 2D Hubbard model. That's a different lattice. And so what you see here is that the resistivity is linear, and 1 here indicates the Mortier-Feriger limit, so it continues to be essentially linear way below the Mortier-Feriger limit. That's the first message. But in this regime where you start going below the Mortier-Feriger limit, it's not exactly linear, first of all. And secondly, the action is no longer entirely in the compressibility. It's actually a joint effect of the diffusion constant, which starts to increase. And the compressibility, this is actually T times the compressibility, so it goes to constant at high temperature, but you see that it starts diving down. So there is an intermediate regime where the product of D times compressibility is approximately linear, but both quantities are temperature dependent. In the case of this calculation, the eventual ground state is a Fermi liquid, so the diffusion constant is going to go like 1 over T squared, and the compressibility, as in any Fermi liquid, is going to be finite. So the resistivity will go like T squared, very, very low temperature. And the statement is that in between there is a regime where the diffusion constant is approximately 1 over T, or at least the product of D and kappa is approximately 1 over temperature. So you see that this crossover from a regime which is dominated by a constant diffusion constant to a regime and a compressibility that runs the show, to a regime in which the diffusion constant increases and the compressibility increases slower than 1 over T, is qualitatively very much what has been observed in your experiment. These are the experimental data from the Princeton group. Okay, so this is the evolution of the doping level in this DMFT calculation. You see this slope that goes like 1 over doping. Now, the thing I want to show you, now I'm going to stick for a few slides with these DMFT results, and I want to answer one of the questions I asked at the beginning, which is, can we actually see what happens to the quasi-particles as we go below the Mortier-Feriger limit? Because the resistivity doesn't do anything. Here, these arrows here indicate the value 1 at which we cross the Mortier-Feriger limit for various doping levels, and you see that the resistivity doesn't do much as we go through that. Okay, so yes.
Is it real that there are 2 slopes always?
So you're asking about this, right? So this is indeed what happens in dynamical mean field theory calculation. This is a very low temperature, right? So it's not totally clear to me that the experiment can still reach this regime, but this is indeed what one finds in the single band Hubbard model solved with DMFT. Whether this is the same in 2 dimensions is not clear. Right.
Because I see the kink and slope, or basically going from Fermi liquid-like to non-Fermi liquid, it actually happens not in the Mortier-Feriger frontier, maybe in half of it. So
yeah, the Mortier.
There is no really sharp point where it should happen. So why do you say there is no change there?
Okay, so what I'm saying is that as you go down here, there is not much happening, right?
There is something just a little bit below.
Yeah, there is something just a little bit below, but what I'm going to show you is that the quasi-particles start appearing way above. So if you look at spectroscopy, so this thing here is not really signaling the appearance of the quasi-particles. But I don't want to make a big deal. I'm very happy if you actually put this Mortier-Feriger limit here. That's fine with me, because you know Mortier-Feriger is defined up to factors of 2 pi. So I don't really care about that. The point I want to make is that there is a very high temperature regime where there are no quasi-particles. There is a very low temperature regime in this calculation where things are Fermi-liquid-like and you have very sharp Landau quasi-particles. And there is an intermediate regime which extends over about a decade of temperature where there are quasi-particles, but they don't have T-square scattering rate. That's the message. And the message is not about exactly where we put these limits. Okay, so this summarizes with colors the message I just gave. There is a high temperature regime where things are way above the Montefiore limit. There is a very low temperature Fermi-liquid regime. In this calculation, in between here, we have a metallic state with non-T-square resistivity and quasi-particles very clearly present from spectroscopic signatures. And I can show you that here. These are plots of the momentum resolved spectral functions, so the thing that you would measure in a photoemission experiment or any outcoupling spectroscopy emulating photoemission in a cold atom experiment. If you are way above, fully incoherent above the Montefiore limit, you see that this thing is just a big blob, which is the lower Hubbard band of this problem. And as you actually enter the below the Montefiore criterion, you see a peak appearing, and eventually this peak is a quasi-particle peak distinct from the lower Hubbard band. So very clearly, you have appearance of quasi-particles as you go through the Montefiore limit. So the Montefiore limit is indeed a proper criterion for the appearance of quasi-particles. They should be detected from a spectroscopic probe. But there is an extended regime of temperature where, despite the fact that you have reasonably sharp quasi-particle peaks in single particle spectroscopies, still the lifetime is not that of a Fermi liquid.
But the peaks are much smaller, right?
Sorry?
So
sure. Sure, they become much sharper in the Fermi liquid regime, obviously, because then the scattering rate becomes very small. Yes. But there is a well-defined peak. I mean, if you're an experimentalist and you're going to measure outcoupling spectroscopy and ask, is there a peak, is there a quasi-particle band or not, you will find one. Then you can negotiate whether the lifetime is T-square or not. That's the point. Okay, so yeah, these are other plots of these momentum resolved spectroscopies. So you see at very high T, you see a big blob, and at very low temperature, you have clearly the lower Hubbard band and a very sharp quasi-particle band. But this quasi-particle band forms at temperatures which are already a fraction of the hopping, so way above the Fermi liquid coherence. Okay, so similar, if you were to measure optical spectroscopy and not just the DC value, you would see similarly signatures of the formation of these quasi-particles. So at very low temperature, you have this Fermi liquid thing. At extremely high temperature in the band metal regime, the optical conductivity is completely featureless. And as you change temperature, there are transfers of spectral weight, which happen between the Drude regime, the Wien-infrared regime, and the high energy regime. And what you see here is that the Montefiore limit is associated with this transfer of spectral weight invading the whole range of energy all the way to several times the Hawking.
This is all for U equals infinity, is that right?
No, this is a calculation for finite U. There is the upper Hubbard band somewhere here is not displayed. It's at U equals 4.
Sigma of omega looks like 1 over omega at the incoherent regime? Or?
Sigma of omega looks like, I don't know what, some Gaussian of some form. I mean, I don't have a characterization of the high frequency regime. Actually, that was the question of Nikolai. Okay, so just to conclude this, and then I'll show you a slide and a half, maybe. This is basically a prayer, not a pledge to the experimentalists. Combine measures of transport and spectroscopy to gain further insight into this crossover from bad metal to OK metal with still linear resistivity. We want to know if you see signatures of quasi-particles, for example, in outcoupling RPS-like spectroscopies below the Montefiore scale.
So you have any comment on all these recent experiments showing linear resistivity down to 0 temperature,
Well,
above optimal doping, which is very different from these calculations?
yeah, it's very different from these calculations. So you know, the thing I want to emphasize here is that the high temperature regime, I think, is well understood theoretically. Now, even in this case, why does the resistivity remain linear, like down to relatively low T, well below the Mortier-Ferrier limit, is not really understood. And so actually, well, I had one slide for you, Subir, I think.
I was going to ask you.
Which is that the only case I know, oops, that's interesting. So my computer seems to be a little bit frozen. The only case I know in which there is a well-documented theory for T-linear resistivity is your model, right? And the calculation we did for transport in the, well, at the time SY model, now SYK model, in which at the time there was a microscopic understanding in a concrete model of T-linear resistivity, which at the time, since this was single band, was producing linear resistivity above the Mortier-Ferrier limit, but in more multi-band versions of this can also be generalized to having linear resistivity below the Mortier-Ferrier limit. So as far as I know, this sort of thing is basically the only thing that provides a theoretical understanding of linear resistivity below the Mortier-Ferrier limit from a microscopic field.
My question is going to be, if you're above the Mortier-Ferrier limit, is there any evidence for the sigma of omega being the square root of omega?
No. Above the Mortier-Ferrier limit, it's all the compressibility that runs the show. That's what I showed before. It's all in kappa. There is no
much bigger than U.
There is no. Sorry.
I thought it was that was equal to temperature is much bigger than U.
No. The compressibility being 1/T also applies when temperature is larger than hopping but smaller than U. And there it's the compressibility that runs the show. Anyhow, so good. So I just want to show one slide about the pseudogap, just a feel-good message for the experimentalist. So it's a completely different topic, but basically the question on the table is, you know, how far are cold atom experiments to actually reaching the pseudogap? And so this is a figure from a recent paper, which is a bunch of authors, including Subir, in which we map out in the temperature versus doping plane, this is cluster DMFT calculations, the pseudogap line, which you see here. And what you see is that at low doping, the pseudogap is reaching a temperature scale which is about 0.2 times the hopping. And this applies to the regime of U for the 2D square lattice Hubbard model, which is anywhere between 5 and 7. So there is a sweet spot region, which is U intermediate between 5 and 7, and no T prime, and low doping, at which temperature of the onset of the pseudogap is about 0.2. And actually this has been validated by benchmarking, by using the techniques that Nikolai was mentioning before, and being able to demonstrate that indeed in this doping regime the pseudogap opens in that temperature range using dynamotic Monte Carlo and a very large cluster diametrical mean field theory. The thing I also want to emphasize is that there is a high temperature phenomenon which is I think very prominent and interesting to reveal again from spectroscopies in cold atom systems, which is that the shape of the Fermi surface is very strongly renormalized by interactions at low doping, in contrast to the high TC community folklore for many, many years. The prediction is that if you actually look at the Hubbard model with 0 T prime at low doping and large U, you'll find that the shape of the Fermi surface is not electron-like, so it doesn't look like this, like the bare band structure would tell you, but actually like that. And that there is a very strong renormalization of the Fermi surface shape. And that should be visible already, according to the various calculations, at rather high temperature. So that's also a call for cold atom experiments. Thank you. Yes. Exactly. Bad metal is not a strange metal. That's exactly the message of part of the talk. Yes. Well, the diffusion constant is a constant, right? So current relaxes with a constant relaxation time. I mean, I guess this is a bit of a semantic question. The commonly admitted definition of a metal in the condensed matter community is something in which the resistivity keeps on increasing when you increase temperature, right? But even though there is no resistivity saturation, so the resistivity continues to increase, please observe that the diffusion constant does saturate, right? So indeed, if you are able to make an independent measurement of the diffusion constant, you will see the Motier-Feregel scale as saturation of the diffusion constant, but not of resistivity. That's because of the exactly, because the number of carriers get very small. Well, there are no quasi-particles. There are electrons, yeah, atoms.
So, I had a question. So, I'm beginning to forget, but there used to be this discussion about statistical versus dynamical quasi-particles, and so the range of validity could be different in temperature range. I was wondering, the fact that you have quasi-particle weight left at higher temperatures, could it be related to the Prangian Karanov or that thing?
Yes, no, you're completely correct. In fact, there is I should have mentioned this in my slide. We mentioned that in our papers. There is a beautiful pioneering paper by Karanov and Pranger, which points out that you don't lose the quasi-particles in spectroscopies as you lose the T-square resistivity. And this is very much, so that was, they did this for electron phonon.
Exactly.
Yeah, absolutely. That's a very good question. And basically, if you want, this is a manifestation of this for electron-electron interactions, so atom-atom interaction.
Yeah, can you give some kind of official and rigorous definition of Fermi liquid? Because some people, including myself, have used this absence or presence of spectral weight at Fermi level as a signature of having or not having Fermi liquid, and obviously in your case you have these quasi-particles. So which quantities one should look at to really define that it's Fermi?
To me, Landau Fermi liquid is a precise statement that you should have single particle excitations that are long-lived and that have a scattering rate that goes like T squared.
T squared, okay.
That is my operational definition. Now, if you relax that, the second condition, right? The point is that you can have sharp, well-defined quasi-particles at scales in which the scattering rate is no longer T squared at all. That's the point. So this is this intermediate regime where we call these resilient quasi-particles.
A question about the plot where you showed like this T star versus doping. How exactly are you defining that line? So you
good question. Yes.
We get a spectral function at
Yes.
the Fermi momentum, and is that just
Yes.
on the disk?
So from this, right? So this would be a measurement of the spectral intensity that you would measure in RPES at the antinode, so at pi 0 in the Brillouin zone. Okay, and you follow this as function of temperature, right? So if you're at high doping, like this curve here, you see that this thing keeps on increasing. You will eventually saturate. That means your quasi-particles become more and more coherent, and eventually you have just a quasi-particle peak. If you actually do that at low doping, like 8%, what you see is that it sort of increases, but then it goes down. So you lose density of states at the antinode. So an operational definition of the T-star crossover, T-star is a crossover, so there are as many definitions as observables. From the point of view of spectral intensity at the antinode, this is the operational definition. It's the maximum of the spectral weight as a function of temperature at the antinode. And the plot I showed before, which is T star versus doping, is obtained by locating this and putting it on this plot.
All right, let's thank Antoine again.